Thank you for the invitation to speak here at the end of January. All right, so I'm going to discuss p-adic families of modular forms. I'll sort of get right to it with the setup. And you'll learn pretty quickly what I mean by upper bounds for constant slope families. So P is going to be a prime. I'm going to write mk for the space of weight k modular forms of level gamma naught p. Okay, so there's a p in the level. Throughout the talk, you could take everything I say and tack on a tame level away from p if you want, but this simplifies the discussion quite a bit, I think. The purpose of having a p in the level and not working at level 1 is to allow p-adic deformations of modular forms. So you need a p in the level to do that kind of thing. On this space, of course, there's Hecke operators, and we'll talk about Hecke eigenforms. And to really click in your brain like that I'm working at level p, the operator is usually written up, and it has an effect on Q expansions like this. Okay, so it doesn't seem to depend on the weight, but it sort of just shifts the coefficients right there. And maybe a classical fact about this operator is that the eigenvalues of up satisfy that they're all algebraic integers, first of all. So when you take their p-adic order for some fixed p-adic valuation on QP bar in which I've embedded the algebraic numbers, you get a positive thing. But also, it can never be any larger than k minus 1. Okay, and that sort of comes from the old form, new form theory. Half the things in here are new forms that all have p-adic valuation k minus 2 over 2, because the eigenvalues are all p to the k minus 2 over 2. And the other half are sort of old forms that come in sort of twin pairs. And from that theory, you sort of see this automatically. And in particular, the AP function is never vanishing for an eigenform of level gamma 0 p. Okay, it's always non-zero. So then the starting point of the investigation is a theorem of Hida in the 1980s, in the special case where AP is a p-adic unit, and Robert Coleman, maybe a decade and a half later, in general. And so I assume that F is an eigenform of weight k and level gamma 0 p, and I mean it's sort of normalized so that its first term of its Q expansion at infinity is 1. And I also need to sort of avoid that top end of the range. Okay, I'll explain a little bit later where that comes up in the way I'm going to phrase things. But you need to sort of delete that one sort of tiny part. Then the theorem of Hida and Coleman says that there exists an F, which I write sort of script and as an infinite Q expansion, an of kappa, Q to the n. Okay, so these are kappas and those are k's because k's have a loop. But an of kappa, Q to the n. And I'm going to refer to this as a p-adic family through F. I need to tell you its properties now. So the first property is telling you exactly what these ANs are. So AN of kappa is a p-adic analytic function on, near k in the p-adic weight space. Weight space. And so I'm going to put a star there just because I'm going to come back to that. Okay, I'll tell you what that is. But whatever it is, it's some sort of p-adic rigid analytic space that contains a point called K. All right? And what that means is when I take this Q expansion, I can evaluate it at K. Yeah? And so the second part of the theorem, maybe I'll just go over here. The second part of the theorem is at kappa equals K. When you evaluate that Q expansion, you get the Q expansion of F. Okay? And the theorem, as I've written it so far, sort of has no content because you could just take F to sort of be the Q expansion that has sort of constant values, the Q expansion of little f, right? And so you need to say something more. And that's really where the family part comes into it. If you take another point in the weight space, K prime, which is an integer, and it's sufficiently large in a way that I don't really want to quantify, then when you evaluate at that integer, what you'll get is something called f prime, which is a weight K prime eigenform also. So this is an element of Mk. It's an eigenform. Okay. And this is the thing that really pins it down. This Q expansion that the theorem says exists has coefficients that are analytically varying in a weight variable. And when you specialize to the weight K or sufficiently many weight K primes, what you recover is either the weight K eigenform F that you started with, the C data, or the eigenform of weight K prime, an eigenform of weight K prime that sort of isn't given to you ahead of time. Okay. So that's what the theorem says. I should be careful to explain what the p-adic weight space is, otherwise it might be hard to understand. So the weight space, I write W, and what it is, say the CP points of it are the continuous characters of ZP cross. Continuous character of ZP cross. Now, ZP cross is a finite group times a procyclic group. And so a continuous character is determined by a discrete parameter, the action on the torsion part of the group, and a continuous parameter depending on a topological generator for the procyclic part. Okay? And what that means is that this is just a union of open unit disks. P-adic disks. Okay? And specifically, a weight here goes to the point, sort of kappa of 1 plus 2p. That's a generator of the procyclic part here, minus 1. That lives in a disk of radius 1 by the continuity. And that's a point in a disk labeled by the action on the torsion part. So I'll just write that, which is a discrete parameter then. There's only finitely many characters of the torsion part of the group. Okay. Put that up. Maybe I will say over here, inside the weight space, you have the integers by taking a weight k and sending it to the character z goes to z to the k. Okay? And this embedding is very nice because it also, like, the integers then get sort of a topology by living inside this open unit disk, and they also have a p-adic topology, and the topology is the same. Okay, so this embedding is, this gives z the p-adic topology. Except you're separating out certain integers by the action of the kth power character on the torsion part. And so that's a congruence mod p minus 1 or something like that. So it's almost the p-adic topology, except you also have congruences mod p minus 1 that you have to take care of. OK. Excellent. And so now this sort of clarifies the theorem. And in part 3, then, the way you should think about part 3 is I'm taking k primes that are highly congruent to k mod p to some large power, and maybe p minus 1 also then, because it has to be near k, so it has to be in one of the same disks, or the same disk, I mean. OK. Now, what is my goal in citing this theorem? So the aim today, actually, I'll put it over here. Is I want to control the size of f. Okay, and what I mean is you're only told that f is given by a convergent Q-series expansion on some disk near k. I want to know how big that disk is, i.e., how near is near. Okay. And the general principle then is like, this is some number that controls the radius of convergence of this family. It's some invariant of the modular form. And there's two possibilities. Either it's a new invariant, which would be interesting, or it's related to other invariants of the modular form, which would be more interesting maybe. And that's sort of the direction that I want to suggest it's going in. Now, I should tell you how to construct these families so that you get a little bit more context. So there's sort of extra context here. Of the what's called the Coleman-Mazur eigencurve. So this is still sort of part of the aim. At a general kappa, so I tell you in the theorem what happens at kappa is k and the other weights that are highly congruent to k. But at a general kappa, f kappa is what's called an overconvergent P-adic modular eigenform, an overconvergent P-adic eigenform. Okay, and such objects, which are generalizations of modular forms, arrange themselves into a beautiful geometric object called an eigencurve that was invented by Coleman and Mazur in the late 90s. Okay, so these arrange themselves into an eigencurve. And this is the work of Coleman-Mazur. I mean, the study of overconvergent p-adic modular forms goes back to Katz in the 70s, but the way in which you can build sort of a rigid analytic curve parameterizing these kinds of objects, and you should say finite slope maybe, is really much more modern than that. And the way it looks, maybe I'll put it here. The way it looks, so this is the eigencurve. It has a C, and there's a weight map that sends a point on the eigencurve to the weight, which sends one of these overconvergent eigenforms to its p-adic weight. Now, the p-adic weight space is sort of a one-dimensional object. It's a bunch of open disks. And so inside here, there's some weight k. And then up here on the eigencurve, there's some point corresponding to f. Yeah? And the theorem says that there's some little family passing through f. That's what this is right here. F looks like that. But the whole context of the eigencurve also has to be taken into account. So maybe I'll erase this for a minute and draw a few more pictures. So here's some other families that are sort of flowing through other points. Maybe I'll make it loop around and then go off. And I'll put dots here and dots here. One thing I want to emphasize is that sort of over each weight, there's an infinite number of points. Okay, so this is not sort of a finite cover of weight space. It's really some infinite degree cover. And then when you're trying to construct a family, what you're really doing, maybe you see I've made some sort of crossing here. Maybe I'll actually do something more dramatic and sort of create a singularity. But what you're doing is you're sort of choosing some neighborhood on this geometric object called the eigencurve on which the weight map is invertible. Okay, so this is like the choice of F. And it's like a neighborhood on which kappa is invertible. Because you see, I parameterize my families by the weights. Right? The eigencurve parameterizes the modular forms, but here I've written everything in terms of the kappas, which are downstairs. Okay, so asking for such a family is asking for a neighborhood of F on the eigencurve in which the weight map is invertible. Okay? Which then, I mean, I say it like that because it's some basic geometric question then that you can ask. And this is where this sort of weird-looking hypothesis enters into the picture. So this hypothesis where you avoid the possibility that the P-adic order is exactly k minus 1 is a hypothesis that guarantees the weight map is invertible at F. And so it's invertible on some neighborhood. Okay. Great.
Sorry. So
Yeah.
If the ord P were k minus 1,
Yeah.
there's still a branch of the
Yeah.
eigencurve that goes through it.
Yeah, it just might ramify. And it's not an if and only if. So when ord P is k minus 1, you're in danger of ramifying, but it's more subtle than that.
And does eigencurve have some properness?
Well, there's some papers that talk about the properness of the eigencurve, but I don't. It just refers to the fact that there's sort of no holes in it, meaning you can't have some families missing. But I don't know really the content of those papers and what properness means in that context.
Oh, yeah, I was just asking if you have holes.
Yeah, no, you can't really have holes. I think they proved this. The first paper was by, I'm forgetting who the first paper was by. The second paper was by Hansheng Diao and Rochuan Liu, I think. The first paper is, I want to say Caligari or Buzzard and Caligari, but I'm losing my memory. Okay, so now this is the basic question, is how big are these families? So let me make it more quantitative. So I'm going to define RF to be the largest disk on which F has a family, first of all. So there exists an F converging on the disk of radius r around kappa, around k. And I actually don't know how to study this quantity. The thing I know how to study is, and such that when you look at the AP function, so AP of F is non-zero, and it's a P-adic analytic function, so there's also some neighborhood on which its norm is constant. Okay, so I also insist that AP of kappa is constant in norm. And I take that disk. So this is called a constant slope family. Slope just coming from using P-adic orders instead of P-adic norms, the theory of the Newton polygon. And this number then is called the constant slope radius. Okay. So what are the theorems that I can prove about this? The first theorem is this. Let's see. Yeah.
When it says converging there, does that include just the statement like 1 or also like the statement 3?
No. I mean the whole thing. There exists an F on that disk.
On that disk, and it has to be a modular form.
Yeah.
Specialized to all those points that are in that.
But that
No.
would be automatic, right?
Yeah.
Because it's forced to be classical by your.
Once you're at that's the sufficiently large. Like at sufficiently large weights, if you force this to be constant, the weights will be much larger than, well, the ORD P of this. And once you're in that situation, the corresponding overconvergent form has to be classical. Yeah. Yeah. Yeah, implicitly throughout the talk, this classicality theorem that Akshay is referring to will come up. I just won't make it so explicit all the time. So the first theorem is a bound like this. You have your AP function, so you can calculate AP of f, which is like AP at the center of the disk on which you live. And then if it's non-zero, you can divide by the derivative at kappa. You get some like P-adic number, I guess, and then you can take its norm. Okay, it's P-adic norm. And this has no content if AP prime is 0. Okay, but okay, so that's the first theorem that I can prove. And before I write the second theorem, I mean, maybe I should say that AP prime over AP, the log derivative of AP, shows up a lot of places in the P-adic theory of modular forms. So there's this famous theorem of Greenberg and Stevens where it sort of first appeared. Okay, so the interest in this bound is like that fact, that this is like an invariant associated with a modular form in some way. The second bound is maybe only for P is 2, but that's sort of a technical issue relating to references that are sort of suboptimal in the state of the art. And it says there exists an explicit function, L of h. So it's a function from, say, real numbers to real numbers. But it grows like c over h as h goes to infinity. And the ratio goes to 1, where c is not 0. Okay, so it's basically asymptotic to 1 over h. And the constant slope radius is no larger than the value of this function on the P-adic order of AP. Okay. So those are the two bounds I can prove. They're proved by completely different methods. This one here, so as AP goes to 0, its P-adic order is going to infinity. And so the function L is sending it to 0. So at worst, this bound says that as AP goes to 0, as AP gets very small, the family has to be shrinking at some rate. Okay? One of the surprising features of this project was the fact that that happens is implicit in nearly every conversation I had as a graduate student about P-adic modular forms. And it's not a theorem that was in the literature. So I was shocked when I proved bound 1, and I didn't know how to prove bound 2. Now, in terms of comparing the two bounds, the first bound is typically much stronger. Okay? I mean that both in terms of if you just heuristically guess what these numbers are, and also by the data. So let me write that down, maybe over here, so that the theorem stays there. So the first bound is typically stronger. This is indicated by data. Indicated by data. And you'll see what I mean by data. We can actually compute these numbers on a computer, which is quite interesting.
How do you compute AP prime?
You compute the ratio AP over AP prime as an L-invariant of a modular form. So I'll get to that.
Oh, you'll tell us.
Yeah. No, I mean, that's important. Like, you can't just compute the AP function on a computer, really. It's some power series on some P-adic disk, and it's hard to do that kind of thing. But these numbers can be computed a different way. The second thing is, without AP prime, one says that RF is at most p to the minus h, where h is the ORD P of AP. And so that's obviously stronger than the second bound, which says that RF is about c over h, which is better than 2, which says that RF is at most c over h. I mean, as h goes to infinity. And And so in that sense, it's a much stronger bound. And whether or not you can ignore AP prime, I don't really know. But the data seems to indicate you generally can, if anything, this makes the bound stronger. Now, what did I want to say about this? So this is actually surprising that the first bound is typically stronger, because as you'll see as I go through the argument, the first bound is nearly trivial to prove, and the second bound lies much deeper in the theory. Okay, which is a bit wobbly because it's much less useful. That being said, there are cases where it typically needs to be taken seriously, where the second bound beats the first bound. Okay, so there is a reason for me to have proven the second bound. Okay. Maybe I'll go over here. Okay, so what is the proof of 1? The proof of 1 is classical P-adic analysis. So let me do us a favor and recenter the disk at k equals 0. Okay, so just apply some isometry of the disk. Then assume you have some f, which is constant slope, on a disk of radius r. Now, part of that tells you that you have the AP function, and the AP function has constant norm. So you look at AP of kappa, and it's given by some convergent power series. Dot, dot, dot. And this converges on this disk, and the norm of AP of kappa is constant. It's constant. Okay, and if anything, maybe I should say this, if anything, the radius of convergence of the whole family is smaller than the radius of convergence of AP. So any bound for how big this can happen is a bound for my radius of constant slope. Okay, so now you calculate. Let's see, so the norm of AP of f is the norm of AP of 0. Okay, so you calculated the center of the disk, that's where f lives. But having a function of constant absolute value is a bit strange, because that means that at the center of the disk and at the edge of the disk, you have the same norm. Right? So this is the same as the sup over the whole disk of any of the values. And on the other hand, you know the P-adic modulus, maximum modulus principle tells you that the sup has to be obtained on the boundary of a disk, not the center of the disk, the boundary of a disk. And in the P-adic world, when you calculate the sup on the boundary of the disk, it's the Gauss norm of this power series. It's the sup over I, the norm of Ci, r to the I. Okay? And if anything, this is bigger than or equal to the norm of C1 times r. And that tells you that r is at most AP divided by the derivative of AP, which is AP prime. Okay, and obviously there's no content if AP prime is vanishing. And so that's what I said over there. Okay. So I sort of really meant it when I said it's sort of surprising that this is the stronger bound, given the methods to prove it are sort of just the maximum modulus principle. But on the other hand, I'm sort of not saying everything in this bound, right? I could have written a different statement here where I use other derivatives, for instance, and it could give you a stronger bound, and I don't know if that's the case or not. Okay. So now before we go on to the second argument, I think it's worth spending some time talking about testing whether the first bound is enough, because the first bound seems so obviously stronger. So how do you test the tightness? If you want to test this bound is tight or not, there's two things you need to be able to do. you need to be able to calculate these radii, and you need to be able to calculate these ratios and take their p-adic absolute value, right? And then you can compare your lists and see whether you get the same numbers or not. So the story goes, how do you calculate these things? So AP prime over AP is, or maybe 2 times this, is what's called an L-invariant. So there's different recipes for how to calculate these things. Maybe what I can say, f is new at p, then the corresponding L-invariant can be calculated from the theory of p-adic L functions. Okay, these are calculated from a p-adic L function. The p-adic L function associated in a new form, when you evaluate at a certain point, has what's called a trivial 0. And when you take the derivative at that 0, the leading term is an algebraic L value that you were looking for with the p-adic L function times this ratio. And so if you have a computer program that can calculate a p-adic L function and an algebraic value, then you can calculate these ratios. Okay? And Rob Pollock, who's one of my collaborators on other projects, has computer programs that can do those 2 things, which means he has computer programs that can calculate these ratios. So this is Pollock, and this work sort of doesn't appear anywhere. There's also, just for the sake of advertising, there's also sporadic small-scale cases without f nu. And so I learned of this when I was in Germany. There's a graduate student at Heidelberg whose name is Peter Graf, and he wrote a thesis about this, and also there's a 4-author paper where they carry out more calculations. And it uses a sort of totally different method, but it doesn't have the so it has the ability to access any kind of modular form, but it can't be done on the same scale as the p-adic L function computations. It's much more computationally intensive. So let me put the data over here now. And I'm going to stick to this new form case. So let me remind you now that the eigenvalue, the UP eigenvalue of a new form is p to the k minus 2 over 2. So the p-adic order is always k minus 2 over 2. Sorry, it's plus or minus p to the k minus 2 over 2. So when I look at the data, I'll take the prime p as 5. I'll take the weight 20. And I'll take the slope h, which is the valuation of up. Oh, sorry, I'll just write down the norm. The norm of AP is 5 to the minus 9th. So I'm going to look at all the new forms. There's 7 new forms. And they all have norm AP 5 to the minus 9th. Okay? And here's what Pollock's data says. So the list of AP over AP primes. Yeah. So the eigenvalue is always plus or minus this number, or plus or minus the number without the negative. And then when you take the norm, you get, yeah. The new forms are all Steinberg at p, and this is somehow that. So the list of AP primes over APs is 5 to the minus 6 twice, 5 to the minus 5 twice, 5 to the minus 2 twice, and 5 inverse once. There's 7 new forms. You calculate these AP prime over APs, and you get these numbers as their norms. And so the first theorem here says at least this.
So, sorry, that's AP over AP prime, right?
Yeah. Which is the thing that's in the theorem. And so the theorem says at least that none of these 7 new forms has a family that lives over the whole disk, which you sort of know because you actually expect only ordinary things to have that property, things where the norm of AP is 1. But it says more than that. It says that at most one of them can have something at radius 1 over 5. At most 3 of them can have families at radius 1 over 25. And sort of the rest of the 4 have to be on pretty small disks, 1 over 5 to the 5th and 1 over 5 to the 6th at best. Okay, the disks might be smaller, but at best you have to be this small. And you can see here these norms are all slightly bigger than 5 to the minus 9th. Okay, so that's pretty good. You can look at this data, and really, when I say the list here, I really mean if you hand Pollock the 7 new forms and you label them somehow, he can label the L-invariants for you. He can really associate them. The more sticky issue for us in calculating data is how do you calculate the RFs? How do you calculate the constant slope radii? And if you think about it, it's quite a problem. Like, you would have to calculate this family, which means maybe calculating all of those ANs up to some P-adic precision, and then test on what their radius of convergence was sort of jointly, which you sort of can't do. Okay? So to calculate the RFs is not really possible, but I can talk about estimating them. Okay, so how would you estimate the RFs? Let me fix H. Okay, and let me define dkh to be the multiplicity of ord P of AP equals H in MK. Okay, so I fix a slope H, or a P-adic norm if you want, and I count the multiplicities of times that norm appears in the space of modular forms. Okay, that's some function that I can generate. It's a function of K. This function is locally constant in K, a variable on the P-adic weight space. Okay, so this is one of Coleman's big theorems about P-adic modular forms, is that if you have 7 new forms of slope 9, then for weights highly congruent to 20, you also have 7. Okay? So as you come into the weight 20, you have 7 things of slope 9. So now start at the weight 20 and start going out. Okay? You used to have 7 forms of slope 9, and as you go out, you might lose some. Okay? Because it's a locally constant function. It doesn't have to be constant. So as you lose some, the places where you lose the slope multiplicity, that might be where the families are disappearing. Okay, you used to have 7 families really close to your weight, and as you move out, you can record the jumps of this locally constant function, and where the jumps occur are where you're gaining or missing families. Okay, so let me write that down now. The heuristic is that the jumps of dkh occur where ord P of APH families appear or disappear. I mean, depending on whether you're thinking of moving in or moving out of the disk. Okay? So in order to estimate the RFs, one thing you would do is just calculate these dimensions and start to see where they're jumping in size. And that's the kind of thing we actually can do on a computer. Okay, so what does the data say there? So if you take the heuristic seriously, in the same situation, P is 5, K is 20, H is 9, the jumps occur. So I'm measuring how far away from 20 the jumps are occurring. Okay. So there's 2 5 to the minus 6, 2 5 to the minus 5s, and then 3 5 to the minus 2s. Okay, which is really close to the previous data that we got from the AP over AP primes. Okay, the only issue is the very largest of these in p-adic size is not quite the very largest of these in p-adic size. This one's a little bit larger. Okay, so that suggests a few things. First of all, it suggests that the first bound is not always tight, because it looks like there's no family that goes to radius 1 over 5. Okay? But it also suggests that except for maybe the very largest possibilities, the bound really is tight. And so maybe there's just like a law going on with these large radii that you have to sort of deal with. Okay. Now let me give you a little bit more context for these numbers. Okay? Because that was something I put in the abstract. And I want to make sure I make reference to it. Okay. And then if we have time, I'll sort of sketch the proof of the second bound. So in 1992, the Gouvea-Mazur conjecture, well, Gouvea and Mazur made a conjecture conjectured that d of kh, that k goes to d of kh, would be locally constant on a disk of radius at least p to the minus h. Okay. In other words, if you went from k, p to the minus h away, you would have the same multiplicity of the slope. In other words, all the families would sort of extend to that radius disk. Now, and so, given that the norm of AP is p to the minus h, the Gouvea-Mazur conjecture is sort of consistent with 1, with the first bound, as long as that derivative has norm less than or equal to 1. Okay. So I sort of wanted to mention that. Now, the sort of rub of it is that this conjecture made in the 1990s suffered from a sort of lack of computers able to calculate things the way that they were able to in the 2000s. And so in 2004, Buzzard and Caligari gave a counterexample. To the Gouvea-Mazur conjecture. Okay. However, it's completely consistent with the bound 1 also. So in this case, this is one of the cases where you can do the small scale calculation. In this case, the norm of AP prime you can calculate as p, okay? Which is enough to save the radius of constant slope to be consistent with the counterexample that Buzzard and Caligari found. So they proved that the local constancy happens on a smaller disk than you would expect, and correspondingly, the bound is slightly smaller than you would expect. Okay? In other words, this I think is sort of very good evidence, sort of hand-on evidence that you can give to suggest why this bound is nearly tight. Okay. That being said, the bound is not always tight. So it sort of behooves us to try to prove a bound that is tight. And so let me try to sketch that argument here at the end in the last 15 minutes. Oh, I should say before before I go on. In this particular example, the second bound on the slope, whatever it is, 9, will produce the 5 to the minus 2. So the second bound, if you apply that, will sort of take care of the error in this particular case. Okay? All right. Now, I did say that the first bound is sort of trivial to prove and the second bound lies deeper. The depth of the second bound is related to Galois representations and their reductions. Okay, so has a Galois representation. Okay, so I'm going to write it VF, and I'll be very specific. This is a P-adic Galois representation, so I'll write meaning over a P-adic field, P-adic coefficients, and I only really need, for the purposes of what I'm about to explain, the local representation at P. So I'm going to study the local P-adic Galois representation at P. And if you have such a thing, you can pick a lattice and reduce it mod P. Okay, and this is now a Galois representation over a finite field, and it's constant in a family. Okay, in fact, the eigencurve breaks up into a finite number of pieces corresponding to a finite set of mod P Galois representations. Okay. And now there's two possibilities. Sort of a tautology. So VF bar is reducible. You can have a local reducible representation, or you can have a local irreducible representation. Okay. And in the irreducible case, for a long time, we knew that there exists a special form for these representations. So there's some integer that's not 0 mod p plus 1. And let me write it here. There's some integer that's not 0 mod p plus 1. And the restriction to inertia, let me just write it, I, is a sum of two characters, omega 2 to the s plus omega 2 to the s times p. S times p, where omega 2 is a level order 2 character of inertia. Okay? Now, you may not recall right away what that is, but all you need to know about it is that it's a character of inertia with order p squared minus 1. So this number s is not sort of well-defined. It's well-defined mod p squared minus 1. And s itself is not well-defined because you could replace s with sp. But like the pair mod p squared minus 1 is well-defined. Okay? So I can talk about the pair mod p squared minus 1 without any problems. Okay. Now, what can we say about these Galois representations? So there's quite a lot known. And the result I want to cite is actually a result from the early 2000s that predates all the advances in the P-adic local Langlands correspondence. But in fact, the calculations that I'll reference were sort of, I've heard through sort of personal communication, were sort of big motivating factors in going further in the early advances. So this is a result due to Berger, Lee, and Zhu. And it says the following. So it says, suppose f prime has weight k prime. And let's write h for the ordered p of a p of f prime. OK, so I want to apply this away from my eigenform f. That's why I'm writing f prime. And you also need to know that f is not new. Sorry, f prime is not new at p, which corresponds to this two-dimensional representation being a crystalline representation. Okay? And then the theorem of Berger-Liégeoux, which is a theorem about crystalline representations, tells you the following. If you knew that k prime was not too big compared to the slope, so it's off by a scalar factor of the slope depending on p. Another way to say this is the slope is very large compared to k. Then VF bar restricted to inertia is irreducible and a power of omega 2 corresponding to k prime minus 1. Okay. So this is actually a completely local theorem about two-dimensional crystalline representations of GQP, and this is what it says in the global context. It says that when you have a comparison where the slope times a factor depending on p is sufficiently large, you can calculate exactly what it is, what this reduction is restricted to inertia. Which is sort of a remarkable theorem because it's not that easy to compute reductions of representations. Okay. And so now what I want to do is I want to imagine I have my eigenform f and it lives in a constant slope family. Okay? And it has its mod p Galois representation that's constant over the family. And I want to think how far do I have to go before I run into this situation where the slope and the weight are in this order. Okay? And if I can prove that I can do that in some controlled way, then like I can try to arrange for my mod p representation not to be this one, and thus my family can't go that far. Okay, so let me write that out. So now consider f fixed of weight k, and h is the ordered p of AP of f. And I look at the following set of weights k prime, which are not the same as k. Oh, in the second bound, I'm assuming p is not 2. So I can work mod p minus 1. And then this condition is just saying that k prime and k live in the same component of weight space. Okay? So that's not really doing anything. The second is that I should arrange for my slope to be, for k prime not to be 2h plus 2. This is saying that any weight k prime eigenform of slope h is not new at p. Okay, so this is ruling out new forms of weight k prime. And h is less than k prime. This is saying that any overconvergent eigenform of weight k prime and slope h is classical. Okay, so now if I had something satisfying these conditions, the weight k prime, any eigenform of slope h, this theorem would apply. Okay? And so then I also assume that k prime is less than p minus 1 times h plus 2, which tells me that my hypothesis in the theorem is satisfied. And so any eigenform of slope h and weight k prime now satisfying these two conditions, I know it's Galois representation. Okay? And so the final condition is just to make sure that this is not the one that f has. So what do I need to do then? Well, this thing is irreducible. So if VF bar is reducible, I don't put anything here. I'm already set. And if VF bar is irreducible, sort of with the s, with the same s up here, then I assume s and ps are not k prime minus 1 mod p squared minus 1. In other words, I'm just assuming that this representation and this representation are distinct. They're different ones. Okay, and so I've already said aloud then the entire punchline. So what you conclude is the following from the Berger-Liégeoux result, is that if k prime is an element of x, then any constant slope family through my original eigenform must miss k prime. Because what I've arranged for is for every eigenform of slope h and weight k prime to have a different Galois representation than the one I have, mod p. But the Galois representations mod p are constant in the family, and so I have to miss this weight k prime. And now you just need to count. Take a weight k prime in here, and you can ask, how close is it p-adically to k? Well, k prime basically lives in some interval. It's between h and p minus 1 times h. So you have some interval that as h goes to infinity is getting larger and larger and larger. And so there's something highly congruent to it, highly congruent to k mod p in there as h goes to infinity. You have to worry that a and d would ruin that you're actually putting some mod p information in there, but you're not, because these are congruences that are co-prime to p. Okay, so when you do this congruence, that doesn't ruin the p-adic comparison in this big interval, and same for this one. So what you conclude is that RF is bounded above by the minimum over all of these weights of the p-adic norms between k and k prime, and that's basically a constant over h as h goes to infinity. That's just some analysis of like how congruent things in a consecutive interval can be to k. It's just some combinatorics. Okay. So maybe that's all I want to say, actually. So thank you for your attention. It was very nice.